In this video, I'm going to demonstrate how to run regression in SPSS. Specifically, this will help you with either simple linear regression or multiple regression. Now, if you remember, a simple linear regression is when you are predicting the outcome of a dependent variable from only one predictor variable, whereas multiple regression is when you're predicting the outcome of a dependent variable from more than one predictor variable. So for this walkthrough, I'll be using the research question, does advertising budget and number of employees predict record sales? So technically, this is going to be a multiple regression, but you could follow everything that I'm doing for a simple linear regression just by using only your one predictor variable. Now, to run the regression analysis, what you'll need to do is go to Analyze, then Regression, and then click on Linear. From here, what you'll want to do is put your outcome variable in the very top box where it says Dependent. So for this example, I'm going to put record sales in this box. Your predictor variables are going to go into the larger box where it says Independence. Now, if you're running a simple linear regression, you will only have, obviously, one predictor variable. But for this example, we have two. So I'm going to move advertising budget and number of employees into the Independence box. Once you've placed your variables into the appropriate area, you'll need to click on Statistics. Here, what you'll want to click on is Collinearity Diagnostics, because this will give you your VIF and tolerance values. However, you only need to click on this if you're running multiple regression. You will also want to click on Durbin-Watson, since this is going to help you assess the assumption of independence. In this area, you can also click on descriptives and part and partial correlations, but I'm not going to here. But you're more than welcome to click on them, and they'll just give you more information about the data. So once you have what you want selected, you can go ahead and click Continue. Next, you're going to want to click on Plots. Here, click on Histogram and Normality Probability Plot. You're going to be able to use these for the assumption of normality. Once you have those selected, you can go ahead and click Continue. Next, you're going to want to click on Save. From here, what you'll want to select is Unstandardized under Predicted Values and select Standardized under Residuals. You're going to use these two to create your residuals plot after you run your regression analysis. Now, the residuals plot can assist you with all of your assumptions, but specifically, it'll help you with the assumption of homoscedasticity. Then go ahead and click Continue, and then click OK to run the analysis. And here are the results. This first box that you see in the output is simply a reminder of what you ran. And then the next three boxes is what you're really going to want to interpret. Now, to interpret the results, you're going to want to go in the order of the boxes and how they're presented, or you're going to want to start with the ANOVA box, then look at the model summary box, and then look at the coefficients box. I prefer looking at the ANOVA box, then the model summary, and then the coefficients. So that's the route that we're going to talk about in this video. So by looking at the ANOVA box, what this is going to assess is if the overall model is significant. If this ANOVA is significant, you can move on to the other boxes. If it's not significant, you will stop and say that the regression model is not significant. However, in this example, we can see that our overall model is significant since the p-value is less than 0.05. So the next thing that I'm going to interpret is the R squared. Now, our R squared is 0.311. So what this indicates is that 31.1% of the variance is accounted for in number of records sold by the number of employees and the advertising budget. You could also interpret adjusted R squared, and really, if there's a big discrepancy between R squared and adjusted R squared, you're going to want to go ahead and stick with the adjusted R squared, because what the adjusted R squared is doing is accounting for the number of predictor variables that you're including in your model. But for us, we're just going to stick with the R squared for now. So the last box that you'll want to interpret is the coefficients box. Now this box will tell you specifically what variables significantly predict the dependent variable and how the predictor variables impact the dependent variable. So in this first row, we see it says constant. Now constant is simply the intercept, and it's not something that people generally care about, but I'm going to explain it a little bit anyways. So if you have a significant intercept, what that generally means is that the intercept doesn't start at 0. It deviates from 0. If it's not significant, then it does start at 0. But like I said, most fields don't really care about it, so we're not going to focus on interpreting it. Now the other two rows underneath that, those are our predictors, or our slopes. So the first row is advertising budget. And we can see that advertising budget significantly predicts record sales. Since it significantly predicts record sales, what we'll want to do is look at B. And this will tell us specifically how advertising budget impacts record sales. The way you interpret this is as your predictor increases by 1 unit, your dependent variable increases by B. So for our example, it is as advertising budget increases by 1 unit, record sales are predicted to increase by 0.067. You could also adjust this phrase by interpreting what units mean based on your data. So in terms of the units used for these variables, what this is saying is that as advertising budget increases by £1,000, record sales are predicted to increase by 67. Now, our second predictor variable is number of employees. However, as indicated by the p-value, this predictor is not a significant predictor of record sales. So you would just simply say that. Now, the last thing that we're going to talk about are the assumptions. Now, there are quite a few assumptions that one needs to check for a regression analysis. The first assumption is the assumption of linearity. Now, for this assumption, what you want to do is to make sure that the predictor variable, each predictor variable, has a linear relationship between the dependent variable. So you would assess the linearity between advertising budget and record sales, as well as number of employees and record sales. However, I'm not going to go over how to do this in this video since I've already talked about it in the correlation video. So go ahead and check that out if you need a reminder. The second assumption that you need to assess is the assumption of multicollinearity. Now for this assumption, you do not want your predictor variables to have a high degree of relationship between them. So you could also check this through the correlations. You don't want there to be a strong relationship, and this can also be found in the correlation video. But another way to check this is by looking at the VIF and the tolerance values. So for tolerance, you do not want that value to be less than 2 or less than 0.2 or less than 0.1. You could decide which cutoff you want to use, but 0.2 or 0.1, anything less than that suggests multicollinearity issues. Now for VIF, you don't want it to be greater than 10. However, anything greater than 1 might indicate multicollinearity issues. So the third assumption is the assumption of independence. And for this assumption, what you're assessing is whether or not the residuals are correlated or uncorrelated. And you want the residuals to be uncorrelated. So to check this, you can use the Durbin-Watson test statistic. And the Durbin-Watson value, it can range from 0 to 4. However, a value near 2 indicates that the assumption is met and that the residuals are uncorrelated. Now, if the Durbin-Watson statistic is less than 2, this indicates a positive correlation. And if the Durbin-Watson is greater than 2, this indicates a negative correlation. So our Durbin-Watson value here is 1.899, suggesting that there is a slight positive correlation between the adjacent residuals. However, this is something that I'm not going to be too concerned about because the Durbin-Watson isn't that far off from 2. Now, the fourth assumption is the normality of the residuals. Now, mind you, I said the normality of the residuals, not the normality of the scores. So we're going to be checking this a little bit different kind of than we would for a t-test or an ANOVA, because for a t-test and ANOVA, all you would do is check the histogram or the skewness and kurtosis for the raw scores. However, to check the normality here, we have to look at the residuals. And basically, for this assumption, you want the residuals to be normally distributed. So to check this, what we're going to do is we're going to look at the histogram and the PP plot. So for these plots, you would interpret them as you would normally. So for the histogram, obviously we want a pretty bell-shaped curve. And for the PP plot, we want the dots to be along the normal distribution line. Now this normal distribution line, it never changes. That normal distribution line is always at a 45-degree angle. So based on the plots that we are provided here, this suggests that we have some issues with normality. Now specifically, if you look at that PP plot, there's the residuals aren't quite on that normal curve line. So the last assumption that we're going to check is the assumption of homoskedasticity. So to check this assumption, you're going to have to use a residual plot. Also note that for the other assumptions that we've discussed, you can also use a residuals plot, but it's just a whole lot easier to check it via the other methods that I've discussed. So to get the residuals plot, you'll need to go to Graphs, and then click on scatter/dot. Now here, you're going to want to make sure that simple scatter is selected. Once that's selected, go ahead and click define. Next, what you'll want to do is put unstandardized predicted in the x-axis and then standardized residuals in the y. And then once those are where they're supposed to be, you can go ahead and click OK. Now to check this assumption, you want to make sure that the pattern of the points or the residuals are in a rectangle shape. You don't want to see a funnel or a triangle shape. So for this example, as you could already tell, the assumption of homoskedasticity is violated. And that is how you run a regression analysis and check the assumptions. If you have any questions, be sure to leave a comment below. But if you're one of my students, just go ahead and email me or text me.